What's the main goal of this presentation? I cannot change the slide. Can you give me this opportunity? Yeah. Okay, so I'll start with the motivation, which motivated our work. So we were working in 3D segmentation, and we were doing segmentation models for body parts. And we realized that there are some crucial challenges. Especially the biggest challenge, as everyone working with 3D data is aware, is high dimensionality of input and output, especially in segmentation task. And another problem is the limited amount of explainability. It's not only in 3D segmentation, it's in any applications that use deep neural networks or any more sophisticated solutions. There are some potential biases which can be really harmful if you are making an AI model which works especially bad for some minorities, then it should not do that, because then we are discriminating some people. So we should try to look at it really deeply. Of course, when you are trying to use AI in medicine, you will always work with doctors, and they have trust issues with black box models. So that's really another big problem with these works. When we are using neural network, you try to give some explanation, and doctors really want to hear those explanations or to be aware of uncertainty at least. And of course, working in medical domain is a high risk domain. You can really influence people. So taking a special care of the safety of your models is really important. Okay, so I talked about attributions, but there are some problems with attributions for 3D segmentation. First, multiple works working on attribution methods only try to work for 2D classification. So for classification or regression, you need a scalar output, but when you are doing a segmentation, you have the same amount of dimension in input and in output. So this makes it a really big problem. But taking it to another step, when you want to analyze how your model works, looking at those attributions and at many images, even in 2D examples, it's really hard to get some idea of how this network works, because you still have to go through all these images which you want to analyze, but maybe skipping like 10 images, you will skip something that's really important regarding how this network works. And now coming to the 3D inputs, when you're having 3D inputs, for example, if there are 512 to the power of 3, then you will see that there are around 10 to the power of 8 voxels. So scrolling through a single attribution, which I did, is really time consuming. For me, it took around an hour to get a good idea of how this model works for a single CT scan. So it's really unfeasible, especially if we take into consideration how important time of radiologist is. So we have to find a better idea how to aggregate those attributions to make our work less time consuming. So this slide is just a presentation of what we try to do. So as you can see, this is aggregated to the power of 2. That's why we have 2 aggregations. But what we are trying to do in our work is going from these fine-grained local explanations, we are trying to aggregate them into interpretable regions. And this allows for a better interpretability just by looking at some numbers. So going from 10 to the power of 8 to, for example, 17 to the power of 2. So much less scale and more interpretable. But first, I said that the attributions are mainly done for classification tasks. So how can we create a simple proxy which allows us to calculate attribution methods for segmentation? So we decided what we are trying to do when interpreting classification models. We are trying to get the idea or try to approximate using input how they created their decision for this classification. So how can we try to make a scalar which is really showing the same for segmentation? So the basic idea is, if you are interested in attribution for a class C, let's say heart, you are then creating a proxy which simply aggregates the logits which were output for the parts of the CT scan which were segmented as the heart. So it's really straightforward. As you can see, we simply create a special mask which shows us where the heart is, and then we are just simply aggregating the outputs of this network to a singular value. There are, of course, maybe it could be done better. So this is one of the parts where you can try to work on this problem, how to go from this multidimensional output to a single dimensional output. So this could be a future work for us. Okay, so now an idea. By having this proxy, as you can see, if you remember smooth grad or vanilla gradient, the calculation of these attributions is really straightforward. After calculating this proxy f hat, then you simply just do the same as you were doing for classification tasks. So that's really straightforward how to calculate that. So now we have these voxel attributions for segmentation task, but we want to know how to later aggregate that. So to aggregate that, we create aggregations for regions of interest, and these regions of interest can be even prepared by some specialists, by radiologists, or they can be, as we have done in our work, simply the classes which our model was classifying. And what we want to achieve with this, so we want to get an idea of how important the specific region of interest was for this segmentation task. So by having these attributions, we are then simply creating these regions of interest mask and creating an aggregation of these voxel attributions. And then we are simply getting a region of interest importance. Like by getting, here we used mass accuracy, it was called. It was introduced in Wojciech Samek work, as I remember. So we decided to use it because one of the important features of using this attribution is that when these regions do not collide, then they always sum up to 1. So this attribution is really interpretable because you know that it always sums up to 1, and you can easily analyze how this network works for different images, because you always normalize to a range between 0 and 1. And of course, after getting these regions of interest importance and having multiple patients, then you can simply create and get an average over all these patients, thus bringing you a global region of interest importance. So for example, you can get the aggregation you can make a sanity check for your network, how it works, by analyzing how important segmentations how important for segmentation of specific regions of interest are important to creating this segmentation. So as you can see here in this image, you can try to analyze how important segmentation of the region of aorta was for creating a segmentation of lung upper lobes. So that's the idea which allows us to create this interpretable features which are much easier to understand for us humans, even if we are not certain about these regions or we are not into, let's say, looking at CT scans. So in our experiments, we used 2 datasets. We used the TotalSegmentator second version, which is public, and we used our B50. This is a cryptonym. It was all private data, which we were certain that there are some people which have really bad lung diseases. So that's why we wanted to test that. And we trained a Swin UNEt model on 16 thorax anatomical structures, and we used 4 attribution methods. And we also, because you can use many attribution methods, and no one has checked whether for this segmentation task, which attribution is most important. So we decided to evaluate those attribution methods. And to do so, we chose 4 metrics. Faithfulness, which measures simply whether the voxel which was selected as important is really important for the segmentation. How to calculate that? You simply mask the most important features and you check how the prediction changes. The sensitivity is simply checking whether a small perturbations in your image changes drastically your attribution. And complexity calculates how complex is your attribution by checking how many attributions are over a specified threshold. So this complexity can be analyzed as, because if there are many voxels which have attribution above specific threshold, it's hard to analyze. When the attribution is localized, so the complexity is less, then it's much easier to try to understand that. And the last was efficiency, and efficiency is simply seconds needed to create an attribution, because it's also important how much of a time you need to get this simple attribution. And we evaluated it on our two datasets. As you can see, the kernel shop had two methods for which we created segments that were used to get this get this attribution method. But the main ideas which we can see is that the most faithful was always vanilla gradient, which was quite shocking for us, because many people say that using a smooth grad or integrated gradients it's much better and it should work better. But in our case, for this task, the simple vanilla gradient was most faithful, less complex than others, and most efficient, but it was more sensitive. So for our later experiments, we decided to use smooth grad because it was bringing us a better balance for faithfulness and sensitivity. And after creating these regions of interest, you can see how easy it is to analyze your network, how it works. So on the left, we have distribution. It's a box plot of these importance scores for segmentation of ribs. And as you can see, the most important body part which was used for segmentation of ribs was ribs. Because when looking at the CT scan, the ribs really stand out because it's a bone, so it looks much different than the soft tissues that are around it. So that we can try to look at those plots to analyze if our networks doesn't work in some specific ways. And on the right, we can see that there is a pulmonary vein, which uses much more information from other regions compared to the ribs. As you can see, of course, the pulmonary vein is still important, but because it's connected to heart, the heart is also really important for the segmentation of this body part. So we also decided to create this global analysis of our model just by creating a specific graph. And this graph was really hard to make it readable, but by using only most important connections, we were able to analyze which parts of the body influence each other. So as I have said, you can use it simply to do some sanity check whether your network works as intended and if there are not some strange connections between this graph. So by having those attributions, we can also check which body parts are segmented by simply using the organ of interest. So how can we analyze this graph? This graph shows how important was the organ of interest important for segmentation of itself. So we can analyze it as how much contextual information, so information outside of the organ we are trying to segment, the network uses to segment this specific organ. And as we can see, the lungs are at the top, so model mostly uses the information from the lungs to segment it, but there are some other body parts which are not so, which use much more contextual information, and this just brings you some information about how this model simply works. But because we created this interpretable region of interest, we were interested whether we can detect some anomalies. Because we have seen that because it can be understood, this region of interest attribution, the aggregated attribution, as some characteristic of how the model works for a specific case. So if we have this characteristic of specific cases, then we can try to find some anomalies in our data. And we conducted tests on both datasets, on B50 and on TSV2. On TotalSegmentator, we had the ground truth masks, so we decided to check whether, if we are getting the anomaly scores, whether it is correlated to the dice score of our prediction. And we found out that for the half of the organs which we were segmenting, the anomaly score was really correlated in the Spearman's test, the rank test. We decided to check how it will work if we try to check the differences of the topmost anomaly scores and bottom less anomaly scores. And these are some examples for lung right upper lobe, and these are examples for this our in-house dataset. And as you can see at the first glance, it's not cherry picking. It was selected automatically because I selected the slices which had the highest attributions, and the anomaly scores were selected anomaly, so it's not cherry picking. You can trust me on that. And as you can see, we noticed that our networks works differently when the patient has some big changes in the lungs. And this allowed us to analyze that when using our network, it works really less predictable when some patients have big changes. Like these changes are most probable. When I was looking at it, they had some kind of operation, or they just had a lot of fluid in their lungs. So by using this, we were able to find examples which our networks works differently, and we now know which examples should be added to the training set to increase its performance on these out of distribution, we can say, examples. Also, by using these anomaly scores, because we have seen that it's correlated to the dice score, we decided to check whether our model has some gender or sex bias. It was a simple test of checking the distribution of sexes in inliers and outliers, and the same was done for age. So we also checked, because we had in our metadata the age and sex of our patients, and we found no statistical evidence for some groups being overrepresented in outliers group. So this is a good thing, because we were able to sanity check whether our networks does not work poorly, for example, for elderly persons. And in summary, our aggregated attribution enables you to analyze your 3D segmentation models. It allows you to do it really efficiently, and these explanations which we create are much less complex, just by creating this easy to understand regions of interest importance, and also by having this anomaly analysis. You can check your model for some biases if you have any metadata available for you. So that's it for me. If you have any questions, feel free to ask, and also don't worry to come and talk with me after.